Hi, everyone. Welcome to the Chameleon webinar. This is going to be the third installment in our Chameleon Cloud webinar series. So thank you very much to everyone who's joining us today. Looks like we got about 35, 34 people in attendance. That's just fabulous. So we're really excited to be here today with you. I fortunately will not be doing most of the talking. I will be listening. We're going to have a special guest today, Ken Raffinetti, who's going to be joined as well by his student Rohan, who put together over the summer a very cool artifact, reproducible artifact that makes it easier to build MPI clusters and other kinds of multi-node experiments on the Chameleon Cloud platform. So hopefully this will be a interesting webinar and maybe even something that you can come back to in the future and use for your own research or education. And it looks like our attendee, our panelist was in the crowd. So I'm gonna allow you to talk, Ken, and put you up here so everyone can see you.
Thanks. Yeah, I've been trying to join, but the Zoom is telling me that I need to use the account that was invited as a panelist. And I don't know what that means. I have one Zoom account. So, uh,
Oh, I'm sorry about that.
so I
I
had to sign.
apologize.
I've been panicking here trying to sign up with my Gmail account. And now I'm here and I'm ready to share if
Great.
give me the
Um,
ball.
of course. Are you able to mute? Are you able to take your camera? Are you able to turn your camera on?
It's not letting me. So Zoom, it doesn't show me that option. I think it still thinks I'm
Oh,
not a panelist.
I see the issue here. Okay. Sorry about this, folks. Just give me a minute or two here to figure out how to get this set up properly. Okay, I just promoted you to panelist, so now you should be able to decloak and share your screen and all that.
There we go.
Perfect. There you are. All right. So I will I will hand it over to you, Ken. I didn't give you
Yeah.
much of an introduction. Ken is from Argonne National Lab. He's a old friend of KK, he PI of Chameleon. And he was working with Rohan over the summer through a program that's related to Chameleon. It's called Repedo. It's a NSF project that's focused on reproducibility in computer science, and they run a cool summer of reproducibility program over the summer where they connect mentors and students to work on reproducible problems or problems in reproducibility, challenges in reproducibility. Anyways, I won't hold it up much longer than that. I'll go ahead
Thanks
and
for
hand it over
throwing.
to you, Ken. Thank you so much for being here today. And I think we're really looking forward to it. Oh, one thing I'll just mention, we are going to be recording the presentation um, so that we can put this online and share, with the public afterwards. However, we will stop recording during the question and answer, so folks can feel free to ask questions in the chat or raise your hand, and I'll unmute you, and then you can ask your question over the chat. So, anyways, I've done enough talking now. I'm going to hand it over to you.
All right. Thanks, Mark. Yeah, that was apologies for the delay. I was planning to join quite early and test everything out, but yeah, the Zoom was proving challenging to join. So yeah, my name is Ken Raffinetti. I'm a research software engineer in the Math and Computer Science Division at Argonne National Lab. So this work, like Mark was saying, was part of the Summer of Reproducibility initiative that was led by the Repetto project in UC Santa Cruz. I'll talk about that in the slides. But the work here was done primarily by Rohan, who you'll also see on the Zoom. And so this was a project that he did over the course of the summer through the Google Summer of Code Summer Reproducibility Initiative. So let's talk about it. Oh, there we go. So first, introduction, just as a background, just going to cover, a very quick high-level view of MPI and HPC in general. So MPI, for those unfamiliar, stands for Message Passing Interface, and it's, the de facto standard, the backbone of high-performance computing. And so it's an interface, it's a programming model, enables efficient scaling across, from laptops, small numbers of workstations to very large clusters. The challenge here, and the reason for this project, is that reproducing MPI-based experiments, research, is a challenging proposition. This is due to dependencies on, specific libraries, network configurations, or just having like a cluster at hand, multiple nodes all configured to work together to launch and run MPI programs. It's not something everybody has at their disposal or can easily access if they're tasked with, trying to reproduce experimental research. So to address this, the goal of this project was to provide some standardized MPI environments on the Chameleon testbed. Users can, I hope everyone here in the Chameleon webinar is familiar with Chameleon. And so I'm not gonna give too much introduction to that. But the idea here is users will take these appliances that we developed and maintain to and then deploy them as a configurable MPI cluster on some number of nodes in Chameleon. The scripts that we developed ensure that everything works together. You're using consistent set of libraries, MPI software, your networking settings, things like SSH are all set up for you. You don't have to worry about that, and just makes things easier to reproduce. Okay, so again, the quick introduction, quick one slide background on MPI. Like I said, it stands for Message Passing Interface. It's something that's been around for 30 plus years now. The MPI Forum organized back in 1992. MPI was, the output of a collaboration between vendors, portability library developers, and users. And their goal was to, incorporate the best ideas of all the different message passing libraries at the time in a standard way. So you have this, you have now an API. Each function takes a fixed set of arguments, and it has fixed semantics. So this standardizes what MPI implementation is supposed to do, and and what the application can and cannot expect when they make MPI calls. Each system can implement MPI differently as long as the semantics match, right? So the semantics are what they are. MPI specifies those, but you can implement it however you like under the covers. And just to be clear, MPI is not a language. It's not a compiler. Despite the fact that, MPI ships with these MPI-CC, MPI-CXX, MPI-Fort compiler wrappers, we call them. Those are not compilers themselves. They're just helper scripts that invoke the GCC or Intel compilers underneath and help you link with MPI. MPI is not a specific implementation or product. So some examples of commonly used implementations of MPI. And again, I want to highlight this because users often are not even aware of there's different MPI implementations. And nor do they know that there are differences between them. But so there's many common ones. MPI-CH or MPICH is the one I work on at Argonne. OpenMPI is another open source, widely available version of MPI. There's also MVAPICH out of the Ohio State team, Intel MPI, Cray MPICH, and many others. So when you log into a system with an MPI, you may not necessarily know what you're using, but if you dig a little deeper, you can figure out, the specific implementation you're using. So prior to this project, MPI on Chameleon was sort of fragmented. There was a number of appliances in the catalog. They were limited to older versions of operating systems, MPI versions, and so it was never clear what exactly you were supposed to use and if it even would work. Um, so when I was talking to Kate, I think last year sometime, I tried to get the complex appliance that I had previously developed. This one here, I don't know if you can see my cursor, but the MPitch 4.2.3 bare metal cluster, and found that it didn't work, and it was hanging during deployment for reasons that I didn't quite understand. And so this is where the discussion led to maybe we should have a student come in and work on this and try and improve the situation and make things better for everyone. So the again, and that coincided with this has been going on for a few years now, but the supercomputing conference, which is the top conference in our field of HPC, has had an ongoing reproducibility initiative for several years now. And just to give background on why reproducibility is important, well, so when you publish research, you want others to be able to compare to it, adopt it, or extend it to build on the work you've done and keep advancing, the state of the art of the field. And so the way the SC conference has been addressing this is that every technical paper that you submit is required to include an artifact description appendix, and this includes the computational artifacts from your research, including software, data sets, environment configurations, things like that, and instructions and documentation for how you're supposed to use them. Now, there's an optional artifact evaluation appendix that has even more detailed instructions, step by step, to reproduce the results of the paper. And each of those evaluation appendices is reviewed by the reproducibility committee. And my understanding is that they are given an allotment of resources on Chameleon Cloud to actually try to run experiments that users submit. So all this being said, there is a clear need for easily configurable HPC appliances on Chameleon Cloud. So as part of the 2025 summer reproducibility, like I said, Kate and I had a conversation. She said, "Why don't you get a student through this? We can facilitate that. It's fully funded, so the student doesn't cost anything to the MPitch project to come in and work on this particular topic." So the background here, the summer reproducibility is a collaboration between this open source research experience office at UC Santa Cruz and the Repetto project. They fund students. It's kind of under the umbrella of the Google Summer of Code, so summer reproducibility or this kind of mentor organization is like a sub-organization under Google Summer of Code, which is humongous. There's tons of participants. And so we proposed a project under that umbrella, MPI Appliance for HPC Research on Chameleon, which matched us with Rohan Babar here, who's also on the call. And so just his background, Rohan, feel free to chime in. You want to introduce yourself, where you are, how you came to join the project, and your background.
Yep, I can. So I am Rohan Babbar. So I graduated with a degree in mathematics and computer science from University of Delhi, Delhi, India. So I live in New Delhi, India. So I'm currently a data analyst at Striker Corporation. Again, I got to know this project majorly because of my interest in MPI, which you can see like I usually try to contribute to different open source projects as well. And mainly I maintain some of them, especially PyLops MPI, which is another MPI implementation getting more into linear algebra and using MPI power in in solving different inverse operations. I also maintain Preliz and Avis plots as well. Before joining this program, I was also a Google Summer of Code student or contributor with NumFocus, especially with PyLops and Arbis. And primarily, you can say I'm interested in scientific computing nowadays, more in MPI programming because I'm just feeling in love with it, and definitely Python packaging. But again, the list goes on and on. Yep, over to you again.
Thanks. Yeah. And so, yeah, so obviously, I'm based in Chicago, Rohan based in India. So it was um, quite quite a long distance relationship, but I think it was actually quite successful. So we found time in the day to overlap for meetings. And Rohan was treated just like any other MPitch student. So we had a handful of other students in the MPitch group this summer, where so we'd have a weekly meeting or biweekly, I guess, where students would present their progress, um, and show what they were working on. So it was quite a good experience on my end. I hope on Rohan's as well to work in this way, and something I would definitely consider for the future. All right. So what are our objectives from this appliances project? So we want to create an MPI appliance that is configurable and easily deployable. So one of the shortcomings of the previous appliances was that they were very static. They were very fixed in nature. They were not as configurable. Um, as was probably desired, and also we wanted them to be functional, and we wanted complex deployments to be functional. So just kind of step by step, pre-built MPI images. We want to create ready-to-use images with MPI and all our dependencies installed. We want that automated cluster configuration capability. So we decided to use Ansible playbooks to achieve this. So there are scripts, Ansible scripts that configure the cluster, do things like the host setup, the SSH key setup, and other configuration across nodes. We want to orchestrate the cluster in a way that you have a template, and so you can scale your cluster deployment from one node to 8 nodes, 16 nodes, whatever you have, and use that orchestration to invoke the Ansible playbooks to make sure everything is configured correctly. And I added a bullet down here, so I just want to give like the simplest possible MPI cluster that you could build. And actually, this is not necessarily the simplest, but this is, in my mind, this is what users more or less expect when you say, here's an MPI cluster for running your experiment. So you've got a login node, also known as like a main or a master node, where you're going to SSH into, and that's going to be the place where you're going to, use to actually like build and run your application. Uh, for our case, we decided to add an NFS share. So this is not strictly required, but it's something that makes things a lot nicer. So if you're going to, you have an NFS share that's mounted on all the nodes in the cluster. And so you can put things like your application binaries or your data there. So all the MPI processes can see the same thing at runtime. So it's just a nice thing to have. You don't necessarily have to have it. You could copy things to all nodes as part of your job, one of your job steps, but NFS makes this a lot easier where you don't have to do that manual copying. You need an MPI installation. Like we said, there's many to choose from, so you need one that's at least there. You can build and run programs. And then the last thing, again, that's nice to have. You could manually do this, but what's much more convenient for users is that there is a pre-populated host file. So when you run MPI exec, right, after you've built your application, you want to run it across, multiple nodes, many cores, things like that. That MPI exec will use that host file in order to launch your job. And so those are kind of like the basic requirements that I was operating from in this project. So our implementation strategy, what did we actually produce? So we selected Ubuntu 22.04 as the base environment. Obviously, I think 24.04 may have been just released at this time, but it wasn't yet maybe the default. Or no, I guess it was a year old at that point. But I think 22.04 was still most widely used in Chameleon at the time, so that's what we chose as kind of the base environment. It had the most compatibility for things like CUDA and other GPU runtimes. We chose Spack and LMOD as our kind of package management strategy. So I'll talk about Spack a lot more in later slides, but the idea here is Spack is a package manager, and you're going to use that to install software rather than the Ubuntu default API, apt package manager. And the reason, we'll get into the reasons why we chose to do that. LMOD or Lua modules is the way we're going to enable users to load and unload various software environments dynamically. When they log into the nodes, that's something that comes integrated into Spack. So when you install software packages in Spack, they generate modules configuration files that then you can integrate into your shell environment and load and unload software very conveniently. Something that's very commonly used in HPC clusters, especially within like the DOE complex that I work in. And so these things together allow you to easily switch between MPI versions, libraries, other dependencies. These appliances we developed, they come with MPitch and OpenMPI pre-installed. So the latest versions that were available at the time when we built the image are there and available for use. Obviously, they can be upgraded or modified depending on the needs of your workload. And we have three different variants. So there's three versions of this appliance. If you look in the catalog, there's a CPU only version. There's an NVIDIA GPU version of the appliance that comes with the CUDA drivers and CUDA runtime 12.8 installed. And there's an AMD GPU version that comes with ROCm 6.4.2. And so this matches the hardware offerings available in Chameleon as of today. So I think there's both NVIDIA GPU and AMD GPU instance types, as well as CPU only. So some background on Spack and why we decided to go with Spack in this project. So it's a package manager designed for HPC. Spack has some nice features, like you can install multiple versions or variants of the same software package and have them coexist, within the same Spack installation. So just as an example, you could have multiple versions of MPitch installed. You can have, the latest, we have 4.3 now, but you can have older versions, 4.1, 3.4, and you just kind of load and unload them at will. And it's very convenient for the user. I would say more so than, and so again, a reason for not using like the default Ubuntu package manager is that more so than the distro or general purpose package managers that, people may be familiar with, Spack is MPI aware. The Spack developers know MPI. They understand the subtleties of MPI, what it is, what the different implementations are. And so that's reflected in its package management tools. It knows how to, swap out various MPI implementations or build MPI applications using one or another MPI. This includes both open and closed source. And so if you're you can use MPitch or OpenMPI. Obviously, you can install those from source, but you can also use things like Intel MPI. Or if you're, not on Chameleon, you're on a Cray system, you can actually, Spack knows how to integrate the Cray MPitch, which is closed source and already pre-installed on a system. It knows how to integrate that and use it to build other Spack packages. So it's very HPC aware. It's very HPC forward. And so that was the idea here with choosing Spack. I think I've already covered here. So we have things like GPU support. So just some examples, right? We can have MPitch. Spack allows you to kind of declaratively state what packages you want to build and what dependencies they have. So you could say build MPitch with GCC and CUDA support. Build MPitch with LLVM for CPU only. These are all things that are supported and very nice to have. The modules integration is great. Like I said, HPC centers rely heavily on modules, including the clusters here at Argonne, like Aurora. And just again, Spack is it's very actively developed. There's tons and tons of packages in the built-in repository. So all from mundane things like development tools, Git, container runtimes, Apptainer, Podman, things like that, and you can even install fully fledged HPC apps like Romax. And the example here shows, you can install Romax, including the MPI backend, and specify MPitch as the MPI provider for that backend. So very, very rich package manager, useful for HPC. The Ansible part. So this is it's funny. I was a system administrator when I first started at Argonne, almost 20 years ago. I don't think Ansible existed back then, but there's lots of configuration management tools to choose from. I think these days Ansible is quite popular. And so this is just some of the background on Ansible. It's an open source project for infrastructure as code. You can automate configuration tasks. It uses this YAML playbook syntax. They don't actually run agents on the nodes that you manage, right? That Ansible kind of goes out, runs the configuration tasks on the node, and then after it's done, there's nothing left over running on the system, which is certainly nice in an HPC context where you want to know what else is going on the system. So for our purposes, we used Ansible for the host setup. So we modified the etc hosts file for all the nodes on the cluster so that they know about each other and how to, what the IP addresses and things are for access. We mount the NFS shares. So Chameleon supports, kind of independent NFS shares. We define those and then use Ansible to mount them on all the nodes. We generate an SSH key pair on the head node so that users log into this head node, and then that key pair for the default user is available and facilitates the launch of parallel jobs on the not just the head node but also what we call the worker nodes. So there's some zero to n number of worker nodes that might also be part of your cluster. We scan all the SSH host keys and update the known hosts on the head node so that you're not prompted with asking whether yes or no you should be able to SSH to this host you've never SSH'd before. So kind of smoothing out the kind of friction points that are typically there if you're trying to build a cluster from scratch. Optionally, you could also use Ansible to manage software. So if you want to, for instance, run additional Spack commands to install software locally on all the nodes so that it's available, you can do that using Ansible. And you can also with that you can update the modules so that when you log into the system, they're there and available for you. And lastly, like I said, we want to create a host file that MPI exec can then use to kind of ingest what the cluster comprised of, how many nodes it's comprised of, and use that as part of the launch process. For orchestration, so excuse me. So say we've got we have this appliance, we have these playbooks to configure it. Now we want to kind of orchestrate this in an automated fashion. We want to launch some number of nodes, generate this inventory dynamically of the head node and the worker nodes, execute the Ansible playbook, and eventually have a ready to use cluster, without a lot of manual effort. So to do that, there's two methods actually. So there's one is the Jupyter Notebooks using the Python Chi library that comes from the Chameleon team, where you can kind of programmatically interact with Chameleon Cloud. And then it uses Ansible. Once it has the resources kind of created and running, then it uses Ansible to finish the configuration that way. And so these are artifacts that you can find the Jupyter Notebooks either in our GitHub repository or on Trovi, where you can actually execute them using the Jupyter runners in Chameleon to build the clusters yourselves. The other option for orchestration is using the Heat Orchestration Template, or HOT, which is yet another YAML-based configuration tool. So it's that complex appliance I showed when you're looking through the Chameleon appliance catalog. So in addition to single node appliances, you could do this complex appliance using heat orchestration. And we fixed the issues. Well, we understand now what the issues were with the previous hot templates, and we implemented workarounds for those so that you can still do that through that interface if you so choose. Yeah, so Mark is posting a link to the artifact and trophy. Right, so the issues we found in the heat deployment previously, the one that I had implemented years ago that was no longer functional, is that I think specifically there was an issue in the key pair module where the OpenStack the complex appliance will fail to launch if you don't provide a public key parameter. As I think, before it supported an auto generation method, but now it's required that you put in the public key. So that was one of the reasons our old appliance was failing to launch. The second one is that this software config module. I don't know if it's unmaintained or whatever, but I think this was the part that it was trying to create that inventory, that dynamic inventory of nodes, and for whatever reason it was timing out at launch time, and so we'll talk about how we worked around that in the later slides. So yeah, actually this is how we worked around it. So instead of trying to fix those heat orchestration template modules, what Rohan kind of cleverly came up with was, let's just launch the cluster with an extra node, what we call a bootstrap node, and then we can use that to run essentially all of the things we would otherwise do in the Jupyter Notebook, which is the Ansible playbooks and things like that. And once it's done configuring all of the cluster setup, then the bootstrap node can go away. And so that's our workaround here. So you set up a bootstrap node, it installs Git and Ansible, downloads the configuration, runs the playbooks, finalizes configuration of the cluster, and basically whatever method you choose, whether it's the Python G Jupyter Notebook or the Heat Orchestration Template, you end up with the same output, which is a fully configured, ready-to-use HPC cluster, right? It uses the same configuration, same Ansible playbooks, and so on and so forth. That your result is the same. Yeah. So this is just summarizing, right? Again, the cluster is launched according to spec and configured using all of the things that we did. Let's see. So deliverables. Mark already linked to the artifacts and trophies. So again, we have our instances, we have appliances. This is the default CPU only appliance based on Ubuntu 22.04. You log in, Spack and LMOD are in your path already, so you don't have to do any additional setup. You log in, you can run Spack commands, you can run module commands, see what's available, and start going from there. There is the CUDA enabled image. So this will be useful if you're looking to run on NVIDIA GPUs. Again, Spack and LMOD are there by default. In this case, the MPICH and OpenMPI versions pre-installed in the CUDA appliance type are CUDA aware. So nothing extra needs to be done to run your MPI plus CUDA application. And there's instructions here at the bottom where you can download an example from the MPICH repository. This is a CUDA plus MPI example where you're calculating the value of pi using the area under the curve, the Riemann sum of the unit circle. And it does that by dividing up the work, and then it farms that work out to the GPU where you've got some number of threads running on the GPU, all calculating their area, their slice of the area in parallel. And then it reduces that from GPU memory to CPU memory and prints it out. So it's a nice little toy example but it proves that your code is running utilizing the GPU and that MPI is able to access that GPU data or GPU memory uh, at runtime. And then like I said, we also have an AMD variant. So especially in DOE labs, AMD GPUs are uh, gaining in popularity, and so being able to do the same thing. I don't have a AMD GPU example of the pi calculation, but if you Google around, you can probably find equivalent types of programs out there. This is the complex appliance we talked about. So this is the if you want to launch the cluster orchestration directly from the Chameleon appliance catalog, this is how you do it. You can launch it at either the Chicago or tax site, and it accepts these parameters. So I think you have to have a lease ahead of time. You probably need a floating IP or something like that to assign to so that the head node has an IP you'll be able to access. And then you just say, how many worker nodes am I going to use? And you can even specify additional Spack packages to install as part of the installation. So that's all integrated into the template. The Trophy artifact, yeah, so this is a Jupyter notebook, or Jupyter Notebooks, I should say, that are examples of so you can run them directly from the Jupyter interface and eventually end up with a fully functioning cluster. So these are also available and there for you to use. The GitHub repository. So where all this work was, was eventually placed when we were done after the summer is in this P models organization, which is where the main MPI development is housed. We have this CCHPC appliances. So this is the canonical source for all the Trophy artifacts. So, if there's changes, issues, you would like to see, report issues here or propose them as pull requests. Just some ideas as potential improvements, things we've talked about but haven't gotten around to implementing, is we could, extend the notebooks to work with other base images besides Ubuntu 22.04. We could add some regular CI testing, so actually run and validate that the appliances are working correctly, periodically, so that things don't end up like they did before, where things break and nobody knows, and then we try and run them and are scratching our head trying to figure out what happened. And also, yeah, another thing would be nice to have is not just regular CI testing, but actual performance and scaling experiments. So if you wanted to, again, prove that this could be useful for running, research experiments, you could try and get a baseline performance, for the Chameleon systems, and see how big you can scale, and if there's any issues with that. So definitely lots of things to do if folks want to pick this up and run with it. So what's our conclusion here? Plenty of time left, so please, if you have questions. But yeah, the work here done by Rohan was done to demonstrate that we can build and configure MPI clusters in the Chameleon testbed and make them easy for users to use. We've got standard images, automation using Ansible. We have orchestration templates, and the end result is we have nodes that are consistently set up, and very little manual effort needed to spin up an HPC MPI cluster for use on Chameleon. Publish the artifacts, so everything's transparent. It's the work is there. Please take it, build it, run with it, extend it. We're very open here, and we want others to use what we built. And yeah, that's it. So please, questions.
Wonderful. Thank you so much, Ken, for the presentation and the going into depth with all of this. We do have two questions from one participant already queued up. They're asking, The first question is using Spack as a program manager and carrying out the installations. Does it work like Python virtual environments with individual packages when used locally?
So I think so. Yeah, let me see if I can understand the question. My, or at least my experience is using Python virtual environments that you kind of install things and it goes into a directory, and then you would like load that whole directory at a time, right? Like you kind of activate that virtual environment, and that becomes part of yours. Spack is a little different where it can kind of piece things together. So you can have like you can